The Story of Quantum Mechanics Part 2. This is a continuation of the story of quantum mechanics as explained in the following sources: Chemistry by Chang and some PDF materials like the quantum mechanical model of the atom, interference of light waves, and de Broglie waves can be experimentally observed. Let us recall from the first video that the Bohr model left many unanswered questions. However, it served as an intermediate model between classical view of the electron and a fully quantum mechanized view, and therefore has great historical and conceptual importance. Before we continue exploring electrons and their behavior, we must first understand a few things about waves. Waves, including electromagnetic waves, interact with each other in a characteristic way called interference. Interference is a phenomenon in which two waves combine by adding their displacement together at every single point in space and time to form a resultant wave of greater or lesser amplitude. For example, if waves of equal amplitude from two sources are in phase when they interact, that is, they align with overlapping crest, a wave with twice the amplitude results. This is called constructive interference. On the other hand, if the waves are completely out of phase, that is, they align so that the crest from one source overlap with the trough of the other source, the waves cancel by destructive interference. When a wave encounters an obstacle such as a slit, it bends. This phenomenon is called diffraction. It is the bending of waves around the corners of an obstacle. At a beach in Tel Aviv, Israel, plain water waves pass through two openings in a break wall. Notice the diffraction effect. The waves exit the opening with circular wave fronts. Notice also how the beach has been shaped by the circular wave fronts. In the same manner, when a beam of light passed through two small slits, the two resulting waves interfere with each other. Whether the interference is constructive or destructive at any given point depends on the difference in the path lengths traveled by the waves. The resulting interference pattern can be viewed as a series of bright and dark lines on a screen. The bright lines are those of constructive interference, and the dark line are destructive interference. The heart of quantum mechanical theory that replaced Bohr's model is the wave nature of the electron, first proposed by Louis de Broglie in 1924 and confirmed by experiment in 1927. De Broglie reasoned that if light waves can behave like a stream of particles or photons, then perhaps particles such as electrons can possess wave properties. He concluded that waves can behave like particles and particles can exhibit wave-like properties. Du Broglie deduced that the particle and wave properties are related by the expression lambda is equal to h over mu, where lambda is the wavelength, h is the Planck's constant, m is the mass, and u is the velocity. The validity of Du Broglie's proposal was confirmed by electron diffraction experiments of G.P. Thomson in 1926 and of Davison and Germer in 1927. According to classical physics, electrons should behave like particles. They travel in straight lines and do not curve in flight unless acted upon by an external agent like a magnetic field. In this model, if we fire a beam of electrons through a double slit onto a detector, we should get two bands of hits, much as you would get if you fired a machine gun at the side of a house with two windows. You will get two areas of bullet-marked wall inside, and the rest would be intact. This, however, did not happen with electrons. If the slits are made small enough and close enough together, we actually observe the electrons are diffracting through the slits and interfering with each other, just like the pattern presented earlier. This means that the electrons have wave-particle duality, just like photons, in agreement with Du Broglie's hypothesis presented earlier. In this case, they must have properties like wavelength and frequency. We can deduce the properties from the behavior of the electrons as they pass through the diffraction grating. This was a pivotal result in the development of quantum mechanics. Just as the photoelectric effect demonstrated the particle nature of light, the Davison-Germer experiment showed the wave nature of matter and completed the theory of wave-particle duality. For physicists, this idea was important because it meant that not only could any particle exhibit wave characteristics, but that one could use the wave equations to describe phenomena in matter if one used the Du Broglie wavelength. For his discovery on the wave nature of electrons, a Nobel Prize for Physics was conferred on Louis Du Broglie in 1929. However, consequent to the discovery that electrons are wave-like, another problem that needed to be resolved came up. How can a position of the wave be specified? Watch for the sequel of this video.